Welcome to the Explainer. I am so thrilled to have you here today because, wow, we are looking at a fascinating paradox unfolding right now in the world of machine learning. If you've been following the industry, you've probably felt like all AI was just merging into this one single massive know-it-all system, right? But looking at the landscape in 2026, the reality is actually the exact opposite. Modern AI is literally splitting into two radical extremes.
So we really have to ask, where exactly is artificial intelligence heading next? For the last few years, we've essentially lived in the era of the general chatbot, that everything to everyone model. Well, that era is officially fracturing. The technology is breaking apart into two very weird, very distinct directions, and it is absolutely going to fundamentally change how we interact with software, biology, and believe it or not, national security. Okay, let's dive into this dichotomy. In one corner, we've got hyper-local edge AI. We are talking about hyper-compressed 1 gigabyte models running completely offline, totally private, right there in your pocket. And then, in the exact opposite corner, we have gated biodefense supermodels. These are massive, incredibly specialized AI systems that are literally plugged into synthetic DNA screeners and being used to brief the White House. I mean, it is a stunning contrast. So here is our roadmap for today's explainer. We're going to look at 1, 2 diverging AI futures, 2, the 1-bit revolution, 3, supercomputing on the edge, 4, GPT-Rosalind's biology brain, and finally, 5, biodefense and dual-use risks. Now, I know, jumping from tech compression straight into biodefense sounds a little wild, but stick with me, it is all part of one unified narrative. All right, part 1, 2 diverging AI futures. We're basically watching the ultimate tug of war here between making AI tiny and free versus making it massive and highly restricted. Let's get into part 2, the 1-bit revolution. Right now, there is this intense mathematical drive to shrink AI down so it can just run locally on the consumer devices you already own. To really understand how they're doing this, we've got to talk about the ternary LMM. Traditionally, AI models use 16-bit numbers for their weights, the internal connections that actually make them smart. Think of a traditional 16-bit AI like this really expensive, complex dimmer switch with thousands of delicate lighting levels. A ternary LLM, though, it restricts those weights to just 3 simple values: -1, 0, and +1. It's basically like swapping out that expensive dimmer for a basic 3-way switch. And because it only uses those 3 numbers, the AI can replace incredibly expensive multiplication math with simple, lightning-fast addition. Because of this, you're going to hear this referred to as 1.58-bit AI. Why that specific number? Well, mathematically speaking, a system with exactly 3 possible states contains the logarithm base 2 of 3, which equals roughly 1.58 bits of information. By totally rethinking neural networks at this fundamental mathematical level, researchers figured out how to compress the intelligence without losing the actual reasoning. And the real-world impact here, it's just stunning. To put this in perspective, a traditional 16-bit, 8 billion parameter model needs about 16 gigabytes of memory just to run. But PrismML's new 1-bit architecture, the Bonsai 8B, only needs 1 gigabyte. That makes the entire model 14 times smaller. Plus, it operates 8 times faster and is incredibly energy efficient, like 4 to 5 times more efficient. You are getting the exact same intelligence, but for just a fraction of the computational cost. Moving on to part 3, supercomputing on the edge. Because, it's one thing to shrink a text model, but it is an entirely different beast to shrink complex visual models. But we have finally broken the memory barrier for smartphones. With the Bonsai Image 4B, these massive diffusion transformers have been shrunk from nearly 8 gigabytes down to under a single gigabyte. The result? You can now generate a high-quality 512 by 512 image on an iPhone 17 Pro Max in just 9.4 seconds. That's wild. The 1-bit version actually maintains 88% of the full-size model's accuracy, and the ternary version hits 95%. And the best part? Because it is 100% local, there's zero latency, and your data literally never touches a cloud server. Total privacy. Okay, hard pivot time. Part 4, GPT-Rosalind's biology brain. We are zooming away from these highly accessible edge models and jumping straight into hyper-specialized, highly restricted life science models. Meet GPT-Rosalind. This is OpenAI's first domain-specific model series, and the timeline for this was blisteringly fast. It was introduced in April 2026, spun into a dedicated biodefense track by May, and then expanded globally to trusted partners by June. The entire goal of this massive model is not to help you write your emails. It's to drastically shrink that traditional 10 to 15-year timeline it takes to get a drug from target discovery to actual clinical approval. It is fine-tuned specifically for the insanely complex, multi-step reasoning demands of genomics, medicinal chemistry, and protein engineering. How does it do it? Well, Rosalind uses a specialized codex plugin layer that connects it directly to over 50 public omics and scientific databases. That gives it an absolute advantage over general AI like GPT 5.5. And crucially, it uses up to 31% fewer compute tokens in genomics. In plain English, that means it reaches the exact same complex biological conclusions with far fewer inferential steps, which ends up saving massive amounts of computational money for these research pipelines. But hey, let's ground these numbers in reality for a second. Even with all that specialized training, GPT-Rosalind still fails 72.5% of complex drug design tasks. That's nearly 3/4, which proves that, at least right now, this technology is an incredible accelerator for expert human scientists, but it is definitely not some autonomous, standalone scientist that's going to replace the lab entirely. We really need to anchor the hype with real-world data here. Get this. Since 2019, over $17 billion has been poured into AI drug discovery. $17 billion. Yet, as of early 2026, not a single AI-developed drug has successfully completed a large-scale clinical trial. Exceptional computational benchmarks on a screen do not instantly equal clinical cures in a hospital. The pipeline is measured in years of biological validation, not just software updates. Which brings us to our final chapter, Part 5. Biodefense and dual-use risks. Because, as you can imagine, a model capable of reasoning over genomic sequences and protein design carries incredibly heavy sociopolitical implications. Back in May 2026, OpenAI formally embedded GPT-Rosalind right into the U.S. biodefense grid, and they laid out this exact four-step workflow that the government and vetted developers are using to prep for future pandemics. The model tackles complex epidemiological modeling, early pathogen detection, it actively screens synthetic DNA, and it develops medical countermeasures. It is a full end-to-end lifecycle defense tool. To really understand why a private AI company is taking this on, we just need to look at the current context of the federal budget. The fiscal year 2027 U.S. budget shows a 44% increase in defense spending, but simultaneously, there's a 12.5% cut to civilian health and human services infrastructure. They even eliminated the hospital preparedness program. So OpenAI is effectively stepping in to offer subsidized access to their models, positioning themselves as this gap filler for civilian health infrastructure while federal funding shifts heavily toward the military. But naturally, this creates a massive structural tension. It's perfectly summarized by this philosophy. Keeping advanced biological AI in governed, accountable, institutional hands reduces dual-use risk more effectively than open access would. Think about that. OpenAI is out there warning the world about the severe risks of AI-generated bioweapons, while simultaneously acting as the sole private gatekeeper of the primary defensive tool against them. They control the model, and they alone control the vetting process for who gets to use it. And that leaves us with a truly fascinating, kind of wild landscape to navigate. On one side, extreme democratization, running a 1-bit supercomputer in your pocket with zero oversights, and on the other, extreme centralization, where the most advanced scientific models are locked tight behind government and corporate gates. So I'll leave you with this final thought. Which path is ultimately more disruptive to our society? The decentralized AI sitting offline in everyone's pocket, or the hyper-specialized AI locked safely inside a biodefense grid? Thank you so much for joining me for this explainer.